everyone. So thanks for having me, Node Interactive. This is going to be awesome. My name is Irina. I am that door, oh my God, okay. I'm a development team lead at Small Media Foundation. I'm based out of London. I used to be out in Vancouver, which is why the Canadian accent, but I live in London. I've made some tough decisions to move from a rainy city to another rainy city. And today I would like to talk about JavaScript and Cellular Automata, or I like to name this talk the hot take on Cellular Automata. So the title's a little bit complicated, and I think we should kind of break it down a little bit and start with a story as to even how I got into this in the first place. So story time. Like I said, I am from Vancouver, and in Vancouver it rains about 99% of the time. And so last November I was out to go for a hike, and our library, which is like this Coliseum-like library, not as cool as this building, but still pretty cool, had a book sale. And the books were like $2 Canadian, which is like 5 € probably. And I picked up this really cool edition of The Hitchhiker's Guide to the Galaxy, and it was awesome, and I wanted to get it. But my partner was sitting there, and he found this little black book, and it said Complexity, a guided tour, and that's all it said. It didn't have like one of those fancy covers to go over top of it, because I think it was lost. So there I was with this book called Complexity, a guided tour, and I thought it was really interesting. And I picked it out, I read the first couple of pages, and it was awesome. And she talks about a bunch of different things that make up complexity, Melanie Mitchell, who is the author. But she also talks about cellular automata in about 10 pages through the 300 pages of the book. And that particular concept kind of struck me, and I thought, okay, how about I explore it? I know JavaScript. I can probably make something out of this, and let's see where it gets me. So I got coding. As soon as I kind of read about it, I thought, okay, let's try this out. And I got to some pretty interesting stuff at the very end, and it was pretty exciting, to be honest. So let's talk about automata. So the original concept kind of came together by the scientist John von Neumann. You might know him from the Manhattan Projects and the things he put together there, but he's also started work on cellular automata, and his kind of series of lectures was called Theory of Self-Evolving Cellular Automata, and that's kind of what started this entire concept and where it got to it. And so when he was putting these lectures together, they were later transcribed by his coworker. He described two kinds of automata, one being kind of the artificial, and the other one being the natural, like seashells and things like that, where certain parts of automata are present. And we're obviously going to be talking about the computer ones. Okay, so I kind of want to know more a little bit. What is it? What is a cellular automata? So as I was reading through his work, I've put together kind of I've extracted the four concepts that make an automata the way he would envision the automata to be. And so rule number one, or like the trait number one, is the fact that whatever the result that comes out of the automata is dependent on how these elementary parts are defined. So it's dependent on how the rules are set, and everything that functions with automata is based on the rules. Second is the fact that an automata must be aware of what's happening around it and kind of what are its neighborhoods like. It must be aware of itself and its surroundings. Three, operations are not directed themselves. So whenever something happens, they're not changing themselves, I guess, if we consider automata as humans. Von Neumann actually did, or like he had like this interesting relationship when he wrote about it. So operations are not directed at themselves, they're transfiguring something else. And it's a decentralized system. And kind of these four different traits that have been put together, we can say that what's super interesting about it is the fact that they produce a much more complicated objects than themselves. And that could be easily seen in something like the Turing Machine, which is an automata. So what starts off with is that you have an automaton that performs the action. The action is basically the automaton punching the holes. The puncher itself is the automaton. And the tape that is infinite in both directions is the one that either has a punched hole through it or an unpunched hole through it. And so the automaton produces the action of actually punching the hole, and the tape is what the result is at. So basically the action that it produces is not directed at themselves, which basically means that entirely the automata itself and the tape and what comes out of it, it's two different constructs, which is really interesting because if you think about it, you're basically producing a much more complicated object which solved enigmas during World War II by simply punching the tape. And that's pretty fascinating to me. So another definition that Melanie Mitchell put together for this automaton was the fact that simple components with local information and communication give rise to coordinated global information processing. So what happens is that these simple rules that have been defined to the cellular automata are basically directing the way the information gets processed. So let's go back to kind of the trait number 2 that we've mentioned previously, the fact that automata is aware. There have been kind of, I've boiled it down to 3 different kind of series of ways that awareness could be structured. And they're based on kind of 3 different people that worked on automata. So one was John von Neumann, who we talked about before. So initially when he was writing doing his lectures on self-reproducing automata, he started off with like this grid, this lattice of light bulbs that he hooked up and he put them together. So I made a replica, obviously, and I think it's pretty close. So basically what would happen is that light bulbs would be connected between one another, and they would be turning on and off based on what their neighbors were doing. So if their neighbors were on per se, eventually the light bulb would turn off. And this was kind of his initial replica, actual hard light bulbs, actual wires, trying to kind of put this together. So then another guy comes in and he's put together something called the game of life, which some of you might or might not be aware. So the game of life was the fact, it's kind of the same grid. You kind of have these light bulbs or whatever it is you want to say. And what happens is that you're also dependent on your neighbors. So I normally describe this example with turtles and koalas. I won't be describing it with turtles and koalas. I was just in Sweden, and the best thing Sweden has is this concept of fika, and I think fika is awesome, so I am going to describe it with coffee and cake, because that's basically fika. So your neighborhoods and kind of your awareness is based on what your neighbors are. So if you're a cup of coffee, you're dependent on kind of your neighborhood, which are the cake. So there's only 2 states in automata. It's a binary state kind of concept. So you can either be one or the other. With a lot of computational papers, you'll have like this concept of dead or alive, so they would just use black or white dots. I just describe it with cake and coffee. So you're dependent on your neighbors, and Conway's game of life works is the fact that you have this giant grid that you will then turn on certain states. You would turn them into that. And then if, basically given this example, if you're a cup of coffee and you have 3 cakes, you become a cake. If there's 2 or 3 cakes around you and you're still a cup of coffee, you stay a cake. And if there are less than 2 of you, you become a coffee. Kind of like that. A little bit confusing, but basically what happens is that you have this grid that changes over time and the grid stays the same. And so a different concept that came out of that was kind of these interesting patterns that you would end up getting. So over time, you would have this glider that goes on and on and on and on and on, depending on how big your universe, I suppose, is. Or similarly, you will have something like the blaster, which looks like spaceships fighting, but it's similarly on this universe of of your automata, and these kind of cells were produced based on their starting position. So with Conway's game of life, it's more of a two-dimensional binary concept that is relevant, but it's two-dimensional because you're looking at the grid itself as your canvas, and binary, obviously, because there's only two states that the cells could take on. So another person came in and he said, okay, this is a little bit complicated, I want to simplify it, and I want to be able to derive certain solutions from that. So Wolfram put together an elementary cellular automata, and he said, okay, so instead of having this grid, instead of having this two-dimensional state that I have to worry about, I just want to think about a one-dimensional and binary state, which basically means that given yourself, you only care about your two closest neighbors. So again, as a cell, you're still aware of your surroundings, and your actions are not towards yourself, but towards others, and you affect everybody around you. But in code perspective, this is how it's going to look like. So you start off with a one-dimensional array, and over time, you're going to progress, and you're going to change as you go along. So you're going to check whether your neighbor to the right who's your neighbor to the right, and then you're going to check who your neighbor to the left might be, and based on who you are and who your neighbors are, you're then able to figure out what it is that you would be in the end. So I think when I started off with this, I just tried to code up rule 110 and see where I get to it. And I was able to kind of replicate something that looks like this. And it was pretty awesome. So the grid would be just like this giant grid that progresses over time, and then you basically explore the patterns that come out of it. So I wanted to look at what exactly is like this pattern that goes on, and then I looked into cellular automata in this particular rule 110, and I realized that, in fact, because the pattern that comes out of it is so complicated and so different, they actually call this particular rule Turing complete. And what that means is that a computational system that can compute every Turing computable function is called Turing complete, or Turing powerful. Alternatively, such a system is one that can simulate a universal Turing machine. So I got this off Wikipedia because that's the first place you go to for things like that. And what was awesome about it is that because these simple rules are, in fact, so simple, you're just dependent on your binary state neighbors, you come out with a quite complicated pattern that takes on. So we've noticed that certain patterns end up dominating in the particular environment, and kind of looking into the pattern as a concept itself, it's basically a set of configurations sharing a common spatial structure. And in particularly with most of Wolfram's 256 rules, it's a dominating pattern that even though a random initial state was initialized, you will still get the same kind of spatial structures every time. So what was then said by a bunch of people who were looking into this is the fact that there is still a diversity of these spatial temporal behaviors, but the system is organizing itself into patterns based on the rules that it follows. And that was really interesting to me that it organizes itself. So I even had 3 slides to point out the fact that it organizes itself into patterns, which is incredibly fascinating. So that leads me to kind of this entire concept that, okay, this entire concept of cellular automata is based on the fact that there is a two-state, two-state kind of concept that people follow, or the automata follow, which leads to kind of this interesting theory of it from bit, which was popularized by John Archibald Wheeler. And what that theory says is it from bit symbolizes the idea that every item of the physical world has at bottom an immaterial source and explanation that which we call reality arises in the last analysis from the posing of yes or no questions. and the registering of equipment evoked responses, which is a pretty complicated way of saying that a lot of this kind of stuff emerges from this binary state solutions, and very complicated things can emerge from binary state solutions. So let's go back to kind of the fact that given these particular patterns, we were looking into this incredibly diverse spatio-temporal behaviors, and the fact that the system is organizing itself into patterns, which, given the particularly simple examples or simple rules that automata follows, we come up with a very complex systems that turn out in the very end. So, and then I guess as I was kind of researching this or putting this together in a sense, I was, I guess, fascinated by this entire concept of complex systems in general. And what is even a complexity or complex system? So I was researching this and I went on the internet, and Google straight up gives me that it's a state or quality of being intricate or complicated. Whereas also the internet, Wikipedia, has put it together as complexity is generally used to characterize something with many parts where those parts interact with each other in multiple ways, culminating in a higher order of emergence greater than the sum of its parts, which sort of starts to make sense in a sense of, or in a position of automata, as a lot of the parts are interacting, and we do come up with something that's a lot greater or a lot more complex than the sum of its parts. But otherwise, I think that still doesn't answer the question of complexity of what it is in the sense or in the space of automata. So another person came up with a couple of questions, and he does really awesome videos about complexity and kind of model thinking, and he's put together 3 different answers, or 3 different questions that we could answer to try to define whether something is complex. And 3 of them are, how hard is it to describe the particular system? How hard is it to create, and what is the degree of such organization? And so I guess that still kind of helps us out with identifying what it is complex and what's not complex, but also not a very standard answer. In fact, I went searching for quite a few more answers, and it seems like folks that study this can't agree on the definition of complexity, much like JavaScript developers can't agree on which framework to use. So I've decided to go back to like the initial stage of this and look into Melanie Mitchell's definitions for complexity. And she says that basically the average information content, or the amount of surprise that you can come up with based on your particular algorithm, is what something is complex. So if you're, I guess, surprised by your result, it's a much more complicated system. And then another one that she's put together is saying that algorithmic information content, or the size of the shortest program to generate complete description, which makes a lot more sense to me as a programmer. So in a sense that anything that becomes complex is then could be, how long will it take me to write something that will reproduce it every time? And so I think with Rule 110, it becomes a lot more complicated to reproduce, because you do end up having such a complicated structure every time that is difficult to reproduce, even though it's based on very simple rules. Okay, so this has been, as I said, like this has fascinated a lot of people, because it's a very simple model that could reproduce something or help people work with much more lifelike models. And so the next thing that people decided to do is that, okay, we have this model that we could write. What happens if we work with evolving these particular cells and see where we get to it? And so why this kind of came to people's minds is because it's a lot, if you look at it, or if you think about it, it's very organic in the way humans reproduce, or things that are alive reproduce, and kind of very similar to genetics work. And so people started looking into it. But the first was kind of von Neumann, and when he was working on his theory of self-reproducing automata, he kind of envisioned this robot. This was very Asimov-like, honestly, for me. He envisioned this robot that basically would be kind of structured in the middle of nowhere, or it would have structure in the middle of nowhere. And what would happen is that it would have access to all the possible different parts it may or may not need ever, and then it would kind of build itself as it required. And as it evolved, it would require more and more parts. And if it were to reproduce, it would require more and more parts, but it would always have this access to the parts. But once people have been putting it together, they decided to simplify the task and see what they could do with like this one-dimensional lattice. So there's work kind of in both one-dimensional and two-dimensional space, and people have been putting together algorithms and genetic evolutions based on both kind of both models, I suppose. And so I kind of like the idea of having a one-dimensional space and seeing where I could come up or what I could come up with in that. So there's kind of three different aspects that one-dimensional things are good at in the beginning, one being density classification, synchronization, and random number generations. And so with density classification is something I decided to look at because that was kind of interesting for me and not simple, but it was straightforward to do and then kind of get to something else at the end. And so the way that would work is basically, it's like a voting system. It's kind of you and your neighbors are about to vote in an election. You have two candidates to vote for, and you want to make sure that your neighbors start voting for your candidate, even though you're starting off in a minority. So you start off with a random state lattice, or an array or a matrix. Random state, again, you're stuck to the binary state solution. And you kind of run the generation over time. So you would have several generations to kind of convince your neighbors to vote for the opposite member. And the goal of this is to make sure that if you're in a minority at the beginning, you want to be in the majority at the end. In fact, you want to win at the end. And you kind of evolve and evolve and evolve. And each one of these items or cells in the lattice start off with a different set of rules. So normally with like Wolfram's automata, you would have a single set of rules that every single one of them follows. But when you perform kind of these density classification tasks, you want each one of them to have a different rule to follow. And then what you end up doing is after each generation, so you might have 140 years in each generation. After each generation, you would perform a fitness level test. And then what you would say is, okay, which one of these rules has performed better? Meaning, in the beginning, if you were one state, you want to be the other state at the end. And if you get there, majority of the time in 150 years, you're good. And then you can kind of have your own metrics as to how much those particular variables could be. So you start off kind of over time, you pick out, okay, so this wasn't very successful because I'm still in the same state over time, but I want to be in a different state the next time around. But basically the concept with this density classification task is very straightforward. All you want to do is being able to convince your neighbors to vote otherwise. And so this kind of thing was interesting to see because in the beginning you would have like this generation 0, which for the most part you would start off with majority black cells and clearly doesn't perform very well because you just end up with a majority of black cells. But it gets a little bit more interesting at the very end because then you are able to see, okay, I start off with more black cells. I'm getting a little bit better, but I'm still ending up with more black cells at the end. And by a certain number of generations, you're able to get to something else. And this is like a very kind of straightforward task for automata to perform, but you are then able to kind of take this down and say, okay, I want to apply this to maybe image processing because I got this whole voting thing down in a basic state, and then I'm able to do something else. So it's like super interesting. I think for me, it's been a super interesting task to kind of see where I get to, because I don't know where I'm going to get to, because other people also don't know where they're going to get to, even the ones that actually study this from time to time. But what happened actually just recently is that my friend and I were at node.js together, and he runs a show called Fun Functions on YouTube. And so him and I have put together kind of an episode of working on this. And what was super interesting is that people keep tweeting at me with all the different things they've built with Automata. And that was kind of the most awesome thing I could have gotten out of this, is that people are actually becoming more interested in something as I guess in a sense rudimentary or boring for a lot of people, in fact. But it's interesting to see that people are becoming a lot more interested in it and are trying these different things out and trying to kind of break some of the rules over time. So I guess what I want you to take away with this is I do understand that for some people it might be a boring subject to take on. I find it fascinating, but I would like you to take it back and explore some more of these kind of concepts of automata and computer science and things like that. I have a compiled list of resources that I might expand on. I want to thank you for having me. I'm on Twitter if you want to say hi. I'm nice. And I will post my slides online on Twitter as well once I deploy it to GH pages. Okay, thanks so much for having me.